Hi class, Miss Womack here. Today we'll be focusing on the unit circle, but first we're going to pop off and just stop for a moment on just a basic investigation into special right triangles, one of which is the 45, 45, 90 degree triangle. Now, this is our rule that's written right up here, and it basically states that these sides of the triangle are always going to be the same, and the hypotenuse is going to be that side multiplied by the square root of 2. Now I'll show you how it works using the Pythagorean theorem below. So if we know we have a 45, 45, 90 triangle, this side, we only have one measure and it says 5. But that would also mean that this side over here would in fact also be 5 degrees. Now we can use the Pythagorean theorem just to prove it real quick. That's 5 squared plus 5 squared. And that's going to equal 25 plus 25, which will actually give us 50. And that's going to be equal to the hypotenuse squared. Now, if we take the square root of 50, that does factor out to 25 times 2. And 25 is a perfect square. So that will be, actually, if we take the square root of that, 5, in fact, will come out of the radical and 2 will stay in. And we do see, lo and behold, 5 root 2 is our hypotenuse. Now let's repeat that over here. Another special right triangle is 30, 60, 90. Now look at what this means. It means that if you have the short side, the hypotenuse is double, and the short leg right over here is going to be this times, or the short side, times the square root of 3. I'll show you how it works. Let's say we only have 3 on this triangle right here, this 3. Well, in fact, we know that it's using that rule, we know the hypotenuse is in fact going to be 6. And we can use a little of the Pythagorean theorem to actually prove that this is going to be 3 root 3. I'll show you real quick. It said we would basically take, and again, using the Pythagorean theorem, a squared plus b squared equals c squared. But we're going to rearrange it a little bit because we are given the hypotenuse. And we'll take 6 squared and subtract 3 squared and see what we come up with. See the difference? 6 squared is 36 minus 9 is actually going to equal 27. And when we take the square root of 27, which does in fact factor to 3 times 3 times 3, or yeah, it would be like 3 times 3 times 3, or 3 times 9. 9 being a perfect square, and when we take the square root of that, the 3 will remain inside, 1 will remain inside, and 1 will in fact come out because 9 is a perfect square, right? So we get, in fact, we do prove that the long side is 3 square root of 3. So we're going to use that little tidbit to help us find a couple of points on our unit circle. So what's a unit circle? Oh, and what are the 6 basic trig functions? Well, we'll be talking about those in a later video, but our unit circle is basically a circle based off of a radius. We're having a radius of 1. Now that means that the measure from the origin that we see right over here to out to the edge of the circle is going to measure 1. So keep that in mind. Now this little picture is very useful because it actually, we can just count because it's broken down into 5-degree segments. And so we'll go ahead and count up, and we're going to go up to our 30-degree mark to do a little trick. So I'm going to go 5, 10, 15, 20, 25, 30. Here's our 30-degree mark, and I'm actually going to create a line from the origin to that 30-degree mark to the edge of the circle. Now that is a special line that we know the measure of because it's also a radius. So we'll establish that measurement already. Now if I have knowledge of my 30, 60, 90, I need the right triangle. Where is it at? Well, we're going to drop a perpendicular line from this point on the edge straight down, or try to at least, until we touch the x-axis, always touching the x-axis. And when we do, we'll create a right triangle, or I'll force it on this one. Now, after we know that, we know a couple of the measurements from what the video said before. We know that the height from here to here is going to be 1/2 because it's half the hypotenuse. And if we do a little bit of presto magico math, we can subtract, we can do 1 squared minus 1/2 squared to find the length of that longer side, just like we just did. So we'll do 1 minus 1/4, and that will give us 3/4. And of course we still have to take the square root of it. When we take the square root of 3/4, using our knowledge of simplifying radicals, we do get this square. We would apply it to both the top and the bottom of our fraction, our numerator and denominator, and we see that our denominator is a perfect square. So it's going to be the square root of 3/2. So what sort of information do we have now? We actually know that this point on this circle right there has a name, and that name, in fact, is going to be the x coordinate. If we go over square root of 3/2, we have its ordered pair. We can identify it. It's the square root of 3/2, comma, 1/2. Now, we'll repeat that again using our knowledge of special right triangles to go to our 45-degree mark. And we'll count 5, 10, 15, 20, 25, 30, 35, 40, 45. So we'll draw a line to our 45-degree, making a 45-degree angle. Again, dropping that and creating a right triangle going straight towards our x-axis, making our 90-degree angle as best I can. Again, I do know that this is 1. If this is 1, then in fact, we're going to have to think about this a little bit differently. What we do know is that these two sides have to match, and when using a squared plus b squared, something strange is going to happen. So what we know is we can actually, usually when we write a squared plus b squared equals c squared, they're not the same, but we're actually going to have to rewrite the Pythagorean theorem just with the understanding that both a and b match. So if in fact they match, then we're going to write it like 2, and we'll just say a squared because there's 2 of them. And how do I know this? Well, I'll back up a little bit because they are actually the same length, and we've seen that before. So I'm going to write them like that, and then I actually can combine those terms, and that will be 2a squares are going to be equal to c squares. So now I know the measure of my hypotenuse. I'm going to set that equal to this new formula that I have. Ta-da! I'm going to divide both sides by 2. And then I have to take the square root of both sides in order to find, because right now it's a squared is equal to 1/2. I actually need to take the square root of both sides. So when I take the square root of both of these, a will actually be equal to, we'll put the square root of 1 over the square root of 2. We're going to need to rationalize that denominator, so I'm going to multiply that times the square root of 2/2, which is 1. And when I do, the square root of 1 times the square root of 2 will be the square root of 2, and these two, when multiplied, will be over 2. We'll practice rationalizing, but there's our pattern. We've established it, and we now know where this point is located on the circle. It is, in fact, the x-coordinate of the square root of 2 over 2, and the y-coordinate the same way, square root of 2 over 2. we'll do one last one, one last one. All right, and we'll count up, and this is 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. And we'll do that one. This is going to be our second 30, 60, 90 that we're going to use, going up to 60 degrees. Going to drop a right triangle straight down through there. And I don't know if you notice, but this is a pretty fair estimate, and you're going to see something interesting happen on this one. Of course, we know that this is 1. This is going to be 1/2. And if you'll recall, a couple of steps ago, we've actually solved this problem already and found this side. Do you remember? Sure we did. We did all the work a minute ago. It just means that things are going to change a little bit. On this one, when it was 30 degrees, the distance on the x-axis was the square root of 3 over 2. But these are going to actually exchange. Doesn't that make sense? It sure will. Now I could do the math, but I know I've done the math over there and it was correct, so I'm going to write the square root of 3 over 2. And then we now know that this point, right here on our unit circle, the coordinate pair or the ordered pair would be, we're going over 1/2, and it actually looks at, if you look there at the bottom, and up the square root of 3 over 2. Now, these are, and two really easy points to find are going to be these position right here. That's going to be to the right 1 and up 0. And make sure you swap those to get to this point right up here, due north, because that's going to be 0, 1. And once we've established that these positions, well, we can do something very interesting. We can actually, with our knowledge of positives and negatives, simply look at a pattern that's created. So if you can remember these 1, 2, 3, 4, 5 points, then you know a tremendous amount about the unit circle. Let's look at it and zoom out and look. Basically, you can actually draw a little rectangle, and these right here, do you see the blue rectangle I'm drawing? They all share the same absolute value, I should say, square root of 3 over 2. However, when you move into the different quadrants where this is positive, positive, to get into that, you know, you have to, this quadrant right here, quadrant 2, would be a negative sign first and then a positive. This is going to be our negative, negative quadrant. And this one over here is going to be our positive, negative quadrant. So by, again, follow it all the way around on that rectangle. Now I'll show you another rectangle here. I'll draw it in red. Here's all of our square root of 2 over 2's. And I'm trying my best to draw that. You can see those points going all the way across on these very special angles at 135, 225, and also at 315. And we'll do one last one so you can see this pattern that emerges. This 1/2 and comma 3 root 2. If you use this, you can create another rectangle to find all of those positions as well. And you actually know the entire unit circle, all because you spent a little time learning these 5 positions. Good luck.